Hello, everyone. Thanks for coming for the seminar today. All right, so today we're having Dario Bettoni. As you may remember, he gave a talk at some point about a year and a half ago. I'm sure you remember all the details about about his professional career, but I shall remind you just in case. So Dario made his PhD in Sisa in Trieste, in Italy. And afterwards, he went on to do postdocs at Technion in Israel, then in Novita in Stockholm, and Heidelberg in Germany, and he's currently at the University of Salamanca. And now let's listen to what he has to tell us.
Okay, so perfect. Thank you very much for coming. Thank you for having me here again. So today, so the talk will affect. So yes, when I was preparing these slides, I realized that the title is basically the last slide I presented in the talk I gave more or less 1.5 years ago. So it's like a natural continuation of what I was presenting you back then. So of course I don't pretend to remember anything about that. So in a way, I will repeat a little bit at least the motivation for what we are doing. So today's talk will be basically based on this paper, which is quite long, I have to say that. But it's also very pedagogical because for me and as well as for my collaborators, so Bertrand and Philippe Brax, was kind of one of the first approaches to this topic, at least in this sense. So it's quite long, but I think it's very pedagogical. So it can be read relatively easily, or you will tell me that. So the topic is a linear response of electrically camouflaged object. What do you mean by this fancy title? Well, linear response probably, you know, it's the same thing as we do for black holes and as we do for tides on Earth. So we have some body and we put an external field and see how it gets deformed. So let's see. So electrically means that it's something going with electromagnetism. And this is just a fancy word to say which kind of screening we are using. No? So basically, we're going to see that our electromagnetism involves some kind of force that we need to suppress with a certain scales. And this is just one way to do so. These are some further readings on the same topic, which are more on the astrophysical topics, aspects of this idea, which if you're interested, you can have a look at. Okay, so just a brief introduction about the motivation of why we are doing so. So the main thing is that gravity is basically the only force acting at large scales in the universe. No? It's a long-range force and it's the only one. So at some point, we can ask if there is the possibility to have other kind of long-range forces. In particular, one could be like the electromagnetic one, which also is a long-range force. Of course, we don't see any standard electromagnetic force, at least on large scales in the universe, otherwise the effects would be devastating for what concerns the large-scale structure, so the universe is neutral in this sense. But still, the question of whether we can have long-range forces is still open in a certain sense, that, for example, for whatever concerns the aspect of the dark sector, dark matter or whatever, could be like charge under some charge, so it would be electromagnetic forces, and in particular, the dark matter could be also non-neutral in this dark sector. So we can have a net charge, which of course exerts force, but still is compatible with what we know about cosmology and astrophysics. So how can we have long-range force in the electromagnetic sense, even though they are dark, so they're not the standard electromagnetism, without spoiling all what we know about large-scale structure? So we need to basically add these ingredients. So one thing is that we need to have a net charge. So if we have a net charge, so we have only plus, for example, we know there will be a force acting between particles or objects, and those will be basically pushed away. However, since we don't see like dark matter halos being pushed away like very fast in our universe, we also need to suppress the force on a small scale, so at least to have some mechanism that is able to say where this force can be active and where cannot be active. And of course, it's involves something which could be cosmologically interesting. We have to have a regime at least where this force is actually doing something. So all of this, the only thing that we need to do is to promote the standard electromagnetism to something which is called nonlinear electromagnetism. So although this might sound a bit fancy and so on, so this is nothing but the same kind of nonlinear stuff we do with cosmological scalar fields. So their nonlinearities are basically everywhere in modern cosmology. The nonlinearities are responsible exactly for fixed forces, which could be phenomenologically very interesting consequences for dark energy, but not only matter and so on. So how do we generalize electromagnetism to nonlinear electromagnetism? Well, simply we promote the standard Maxwell-Lagrangian to a generic function of these two, which are the Lorentz invariant quantities that can be started from the electromagnetic tensor. One is standard F mu, which is the Maxwell term, and the other one is the dual, which, as you can see, involves the product between the electric and the magnetic field. For what concerns this talk, I will mostly be focused on static configuration. So we're going to have the picture of having some spherical object, which is static, and we see what happens when we switch on an external field. You can even imagine at some point, I will also slide about this. You can really imagine to have an experiment, so you put some external field, and you simply watch how your spherical object is being deformed. So that is basically everything we're going to do throughout this talk. Okay, so at some point you can say, okay, I have just a generic nonlinear function. You say, okay, with that we cannot do that much, especially if we want to do calculation. We need to specify a little bit which kind of Lagrangian we are actually interested in. And symmetries, typically in this sense, come to rescue because, for example, so if you take Maxwell electromagnetism, you know that it shares two symmetries. One is conformal invariance, so you see, basically associated with the masslessness of the photon. And it's basically can be seen, for example, there are various ways to see, but for example, can be seen as the vanishing of the trace of the energy momentum tensor. But also it possesses a different symmetry, another symmetry, which is called the duality invariance. So basically it's invariant, that is, equation of motion are invariant under rotation in the sense. So you can actually rotate, and this gives you the equation of motion invariant. There is a duality invariant. This, for example, is associated to the conservation of helicity of the photon. Because none of this is actually strictly necessary everywhere. For example, the breaking of conformal invariance in inflation can actually allows you to have primordial magnetic fields. In this sense, you can have helicity different chirality in the photon. So how can we generalize this in a nonlinear sense? So recently there was one direction. So there were these people who proved that there exists an extension which is nonlinear of Maxwell electromagnetism that shares the same symmetries as Maxwell. So you have duality invariance and conformal invariance. And this is called the ModMax electromagnetism. And then there is the famous Born-Infeld electromagnetism, which is quite old by now, but still is very fashionable, and for which the conformal invariance is broken. Why do we need to break somewhere conformal invariance? Because we want to have a scale which is separating the regions where you have screening and where you don't have screening. So every time that you want to have a scale for doing for separating regions, you need to have a scale, and this scale will basically break conformal invariance. Summing everything up, the model we're going to look for is this very long name, Born-Infeld and ModMax. So you take ModMax and you make it similar to what is Born-Infeld. And this was done by in this tutorial. So how does it look like this Lagrangian? Well, this Lagrangian looks like this. Can be seen a bit complicated, so many terms, but as you can see, basically you still have the y square root of a square, so you have both contributions. They're suppressed by a certain scale, which is the thing that we want to separate regions where we are screening or not. And this gamma is just a parameter that is responsible for the ModMax extension of Maxwellian electromagnetism. As you can see, if gamma goes to 0, basically you recover Maxwell in this situation. So basically the limit where lambda goes to infinity of this action gives you ModMax, and if you set also gamma to 0, you recover Maxwell. And this happens in the same sense in this way. If you go from this action, you take the limit of gamma very small, you get the Born-Infeld action, and if you then send lambda to infinity, you will get again back to Maxwell. So these are actually theories that have Maxwell as a small field limit. Okay. So this probably is the only nonlinear electromagnetism sharing the same properties of ModMax, and this is one field which has. This is very peculiar. As we'll see later on, this has very peculiar properties which are not completely understood yet. In particular, for example, there is the absence of the refringence in this kind of models. So, Born-Infeld is very, very special in the context of nonlinear electrodynamics. So what can we do about this? Well, first of all, I will focus on background static solution. So I want to add my theory, and I simply want to see what happens when I look at static solution. Well, despite being very complicated, the Lagrangian you've seen before, this admits in this context where we're looking at static solution, it has a very simple and analytical solution. So this is the solution we get for electric field once impose spherical symmetry and once we neglect the magnetic fields. Since it's static, we do not expect this to be generated. It's a bit more subtle than that, but still, this is a consistent solution of our equation of motion for the spherical and static case. Okay, this is relatively simple. This Rx is simply just the dimensional quantity, which is the radius scaled by the screening radius, which is given by this expression, where Q is actually the charge contained into my distribution of mass, and lambda is the suppressing scale. Okay. Of course, when you take the limit to the small radii, as you can see, you get a constant value. So this basically means, as compared with the typical Maxwellian behavior that is divergent, it tells you that you are basically screening your force. No, you're screening the electric field, so you're screening the force acting on particles. So below this screening scale, you have a constant electric field. Of course, at X radii, as you can see, you recover the typical Maxwellian behavior that goes as 1 over x squared. So you have basically standard electromagnetism. With the only difference that in this case, we have kind of a global redressing that is given by this gamma parameter. If you set gamma to 0, exactly you will get Maxwell, and here we actually get the result from Born-Infeld. So you see that the skinny radius, basically what it's doing is splitting into a region where you screen, where you suppress the force, and the region where you recover the Maxwellian behavior at the lambda.
That's Born-Infeld or ModMax?
Okay, so this limit is, so both limits are, in this case, is the ModMax version of Born-Infeld because of this gamma parameter. But this is a typical behavior that you expect also in Born-Infeld, that the scale where the electric field goes to a constant. And this behavior is retained also when you generalize to the ModMax. And the other interesting thing is that you can actually solve this equation for a set of charges. So you can put a set of charges, you can actually solve for distribution. And what we find is the following thing. So if we have the electric field generated, the displacement, which is given in terms of a sum over the charges of the single particle and the relative distance. It's a standard electromagnetism. The only difference is that the electric field is given by this more complicated expression. So on the left, we have basically a monopole, and the purple circle is giving the screening radius, and this color code is giving where the field, so the darker is where the Maxwell behavior is growing, no? Because since the ratio is K minus 1, so we're basically where there is a largest difference between the Maxwellian behavior, while the lighter color is where basically we are having the same behavior as Maxwell. So this, I said, is a screening radius. As you can see, when you have a monopole, you have basically a screen charge. What is interesting is that if you increase the electric field, external one, so here you have an external field, you're increasing the external one, as you can see, you get the displacement of the screening region. So the screening region shifts along with the same direction as the external electric field. On the other side, what is interesting in this case is we are taking a dipole, but it's made by two alike charges. Okay, so the two charges have the same sign. So as you can see, if both charges rise outside of their respective screening radii, as you can see, they are, although they are touching, they are not overlapping. Okay, so as you can see, the effect is of course a repulsive force. So as you can see, the effective screened region is deformed between the two objects. And it's a typical thing when we respect to have different charges. Okay, so but the other interesting thing is that once the two charges are actually inside the screening radius of each other, as you can see, they basically produce like a global screening region with the peculiarity that you might have regions inside where the screening ceases to be valid. Okay, so where they're breaking the screen, you see this lighter area is telling you that there you are basically covering the Maxwellian. So which is something that is interesting, and we were not aware of other studies related to this in this context. So it was interesting to point this out. So far, basically, the astrophysics, and I will now switch to a slightly different topic. And how you forgive me if in this talk, basically, there will be no gravity, it will be electromagnetism. But I will closely follow something that people do, especially when dealing with black holes. It's exactly the same thing. In fact, we and other researchers took inspiration exactly from the theory of log numbers and so on to derive the same quantities, but in the context of spin one field. Okay, so here, when you think about external field, it's not a gravitational one, but it's an electric field. So far, what I wanted to focus is that we might have astrophysical situation where this is realized, and for which we actually can also have solutions for. Now, since we have seen that we have stable and viable background configuration, so we took like a sphere. Now consider just a monopole. We take a sphere, we take a charged particle where this its screening radius associated, and so on and so forth. So all these quantities, ky and so, are background quantities, and we know them explicitly when we select a particular theory. No, in this case, we will focus on this Born-Infeld and ModMax. And simply what we do, we take this typical thing, we take the second order actions. We expand perturbation up to second order. And from here, we want to do the typical things. We want to check the absence of ghosts, and the absence of Laplacian instabilities. And we want to be sure that we have subluminal propagation of our perturbations, which is not something which is granted once I go for nonlinear theories. There, I have to check all of these. And so in particular, the absence of ghosts requires that this function is greater than 0. So this is, for example, here. And also, we have to have this combination to be greater than 0, as you can read from this coefficient. Furthermore, if you want to avoid Laplacian instability, typical gradient instabilities, we simply have to look at what happens to the magnetic field term. And of course, this requires also this combination to be well, positive quantities. Okay, y must be greater than this quantity. A little bit more subtle is if you want to check whether the propagation speed of the photon, the one associated to the polar and the axial modes, are actually smaller than the speed of light or not. So from the graphics, you can immediately tell that this is the case, at least for this kind of theory, but you can see that in fact they have at large scales, they recover the Maxwellian behavior, with the only difference that while the polar is exactly Maxwellian at that scales, the axial gets suppressed because of the presence of this gamma factor that comes from the ModMax implementation. And then when you go to smaller scale, you see there is a drop. To cut the long story short, it's just to show that we did this calculation, that we actually ensure that we have subluminal propagation. So in one case, we can compute this quantity, and we see that this is a certain requirement. And since we expect y to be a decreasing, monotonically decreasing function of radii, it's basically the electric field. We expect it to be decreasing when we go to larger distances. We know that this quantity is negative, cancel the minus, and then this quantity needs to be positive. And this implies that the speed, at least for the polar perturbation, is smaller than 1 always. The axial one is a bit more subtle because we don't know anything about this contribution. However, if we impose the duality, so if you remember, I was taking one of the symmetries I wanted to take care is this duality symmetry that possesses Maxwell and also is preserved in this ModMax situation, then this duality invariance imposes this condition. It's telling us that the axial propagation speed is actually proportional to ky to the -2. So this, of course, is smaller than 1 because remember, ky is the suppressing scale in the electromagnetic. So it interpolates between 0, Maxwellian, and 1, suppressed. However, as you can see, when this quantity goes close to 0, when this is basically non-linear, we could have a potential problem of stroke coupling because the smaller is this ky, the larger becomes the bigger is ky, the smaller becomes the speed of sound. And this typically is related to the strong coupling problem. And this is typical of dual theories because typically when you have dual theories, if you are perturbative in one sector, when you go to the dual, the perturbation parameter goes 1 over it, and so it becomes strongly coupled. But this is something that happens. Nonetheless, this is something that also occurs in scalar tensor theory. So when you have scalar with the same screening mechanism, with the difference that in this case we are subluminal, while in the scalar case they are superluminal. So for the scalar case, it's actually worse the situation. Nonetheless, this might just tells us that we need to be slightly more careful when we go to this high nominal regime, but it doesn't impede us to keep on with our analysis. So, yes.
Can you explain what is going on in the action? Or, for example, there's this term with kappa ZZ.
Yes.
So how does this come about? Because there's a y in front, so I would think maybe you do some kind of expansion in y, and then you get, so I suppose the d, that's for derivative.
Yes, of course. The subscript in this case refers to the derivative with respect to one of the two arguments of the function.
Yeah.
And this is this is the way you can write this in terms of electric and magnetic fields. What you should do is you should take your 4 vector A mu, decompose it into the A0, A radial, and the spherical components. You should write in terms of that your second order action, and then compute all the coefficients. So we did that. So we do the full calculation to realize that this, and actually the reading of this propagation speed from here might sound a bit unwavy, because I'm telling you, okay, you just take the angular versus the radial in the compute, and you get the axial, the polar component. But we actually carefully did this by properly expanding the proper degrees of freedom, choosing the gauge, and so on and so forth. And we actually checked that this is actually the speed of sound. But anyway, so this is just a slightly different way of rewriting an actions at the second order for a generic electromagnetic field. So we did, so in the table we did all the calculation in appendix. I hope I answered the question.
Okay. My second question is the figure down below. So what are these different terms?
Yes, so the red one refers to the polar speed of sound, and the green one refers to the axial, and the change of color depends on the value of the gamma parameters. So the bigger is gamma, the more suppressed is the speed. So as you can see from here, so the polar is basically this behavior. So a large scale it goes exactly to 1, a smaller scale it goes to 0. And if you read CA from this, you will get it A to the -2 gamma, which is suppressing with respect to the other. And in fact, as you can see, for example, the Born-Infeld case is gamma equals 0, and then you recover the fact that both propagation speed are the same. Okay, so since we are perturbing around a static spherical symmetric object, our equations simply can take this 2. It implies that as usual, we can decompose this in terms of 2 scalars. One will be the axial and one will be the polar scalar. We can write the equation for the perturbation, which is just I just put it because it's a simple and useful redefinition. As you can see, it appears the speed of sound, the two different, and here the difference is that there is a different sign, plus and the minus. But this is just standard thing. You compute you expand your action, you compute the equation, and then you want to investigate what your equations are going to tell you in this case. Of course, since we are spherically symmetric, we expand in spherical harmonics. Actually, these are vector spherical harmonics, so it's a bit more lengthy, a bit slightly more trickier to derive this equation, but nonetheless, these are the 2 equations. As you can see, they are simple equations, basically oscillators. No? However, there is the mass will depend on the coordinates and will depend on the angular momentum in this polar case, and also will depend on the gamma coefficient in the case of the axial. So once you have your equation, here we are plotting the masses. As you can see, the Born-Infeld is particularly interesting because if you follow, so the color code is red, orange is the polar, and green, yellow is the axial for 2 different components. The dashed line here is the Maxwell, okay, evolution of the masses. As you can see, both axial and polar are the same and goes diverging towards 0 as expected. While for the Born-Infeld, as you can see, they do not overlap the 2. While if we switch on this gamma parameter with just equality, as you can see, the axial one crosses also the other one. So there is a modification that affects the masses. In any case, the only thing is that we have derived our equation. Remember, we are trying to study how a system responds when I'm stimulating with external electric field. We have our equation, and we need to solve our equation somehow. These are not very complicated. In fact, one can show that these basically are nothing but hypergeometric functions, the solution to this one. So you can actually get fully analytical solution. So at this point, I will focus more exactly on what is the topic of this talk. So,
There's a question.
sorry. Ah, okay, sorry. Yes, exactly, because you're seeing that this mass is becoming negative. So as I was checking the previous one, the system is stable. So we actually were worried at the beginning about this negative mass, but since it goes to zero and it's just a transient, it should not be associated to any tachyonic or instability. Yeah, but thanks for the questions. But we were worried and we checked, and that's why we also did all the previous calculations to be sure that our theory is actually stable. Okay, so what we're doing basically, okay, we just take our object, we have some plates that are potentially in charge, and once we charge, we know that the object gets deformed, the charge is moved towards one side. But the other interesting thing is that not only do we have an external field, the deformation in our object will contribute at infinity, if we take this infinity, no, with adding some other multiples. So once you have the external field that can be set from, for example, setting it at the boundaries, the object gets deformed and it responds at infinity again, adding some other multiples. And it's exactly this what in the case of black holes are called the love numbers, in the case of electric fields are called magnetic susceptibility or polarization, electric polarization. But this is the picture I would like you to keep in mind to follow the next discussion. And remember, it's basically electrodynamics, although it's slightly more complicated because we have non-linearity. So what is the linear response? Well, basically, it's exactly what I told you before. So imagine that we have our blob of. So let's say that our blob is actually something which is slightly ephemeral, so maybe because we have a point particle, and the blob is represented by the screening radius. So while in the case of black holes, we have like the horizon, no, as the size of your object. In our case, the size of our object is the screening radius. We could have studied extended object, but we left this for future work. So of course we take inspiration of black holes, and that's exactly what I told you. Tidal field induces deformation in the body, and this reacts adding other multiples moments at gravitation, so to the gravitational field at infinity. You can see from here. So this is basically the gravitational field produced by a spherical source, and on top of this we are adding one, which is basically the external field, plus, and here we have extracted epsilon L, which is the external field. So this is basically the ratio of the induced multiples over the external one. And these coefficients that we have in front of here are exactly the log numbers. And this is Mr. Log. Okay? So we want to do exactly the same. So we're asking the question whether we can actually do the same for our situation. So why log numbers? Why this might be interesting? Well, because we know that in the context of black holes, and not only, but not generally of neutron star or compact objects, these quantities can be accessible, for example, via gravitational waves. So we can actually access the information about the properties of an object through this coefficient. And also we know that black holes are rigid. So it's something quite interesting, because it doesn't matter that you perturb at infinity with tidal fields, the black holes will actually not get deformed, at least in 4 dimensions. And for uncharged black holes, I think. So for Kerr, it has been proven, and for Schwarzschild as well. I'm not sure about charged one. So then the question is, what happens if instead of having a black hole, we have our screening radius, and instead of having gravity, we have electromagnetism. But that's what we get. These are the solutions that we get from the previous equation I showed you. So remember that typically when you want, there is some subtle thing. So typically when you want to compute these numbers, you have to impose boundary conditions. And so what you impose is the regularity of your solution at the black hole horizon. So in this case, what we did was to impose the regularity condition at the origin, because there at the origin, the field is finite. So it doesn't diverge, because the nonlinear electromagnetism is actually suppressing, making it constant. So we can actually take boundary condition exactly at the origin. These are the solution. As you can see, we have the only reason why I'm plotting this, because we have the decay and the growing. Okay, so these are the two things. So we expect to have the external and the reaction. And we can compute as a ratio between the two, we can compute the electric polarizability. As you can see, the electric polarizability has this complicated structure, but few things that might be interesting to point out. For the dipole, This goes as the cube, so the radius of the cube, so it goes as the volume, exactly as in typical standard electromagnetism. And then you see you have this complex combination of gamma functions. So I don't know if you remember, but the reason why the log number vanishes because you cannot find regular solution at the horizon. So there is no regularity at the horizon at infinity. So you need to. This implies that it's one of the two. So if you don't have one of the solutions, it implies that since this number are the ratio between the coefficients, if you don't have one, those must be zero. Okay. So and what is interesting is that if you look at the poles in this gamma function, you can realize that this electric polarisability vanishes for odd moment multipoles above the dipole. So up to the dipole, you have electric polarisability. So if you put a dipole, you will deform this object. You will see electric polarisability. But if, for example, if you put n equals 3, this is completely transparent to this kind of perturbations. So this is basically what it's telling us. So the fact that it's vanishing, it tells us that with respect to this kind of multiple structure, our object is transparent. It doesn't get deformed. So this was actually done late in the 90s, but we kind of extended, and especially we identified the whole structure of multiples, that which is vanishing. Okay, and also we did not only for the electric polarisability, but also for the magnetic susceptibility. This again simply is related to the axial sector. Since we have two sectors, we have the polar, which is the polarisability, and the axial sector gives you the magnetic susceptibility. In this case, we get basically the same, slightly more complicated because we have this gamma factor here. But the concept is basically the same. We have a increase in lowering mode, and we can compute the ratio. We can look for the poles in this gamma function, and if we have poles, then it gives us where the magnetic susceptibility vanishes. Of course, in this case, where you can see that basically this effective multipole is a continuous quantity because gamma is a continuous parameter. Generically, this will not vanish unless you go to the Born-Infeld case where gamma is equal to 0, and then this becomes 1. And then again, you will find that in this case, the magnetic susceptibility vanishes for the even numbers. Okay, so that's what we get. This is just an interesting consequence of that. You see that the tail is basically going up to the minus L, and both align perfectly on a single line, where we see that they alternate, where one is 0, the other one is not, and so on.
Is there a simple explanation for this one?
Yes, which I'm gonna tell you. For the vanishing, I will try to. Well, I don't know if it's simple, but I will try to follow because you see, so far this vanishing simply comes out from the solution of the equation. You get the equation, you solve, and you see that those numbers vanishes. So the question is exactly. Can we try to understand this problem using ladder operators and conserved charges, which is something that people do in Marco. Very briefly, what are ladder operators? So we do the following strategy. We have the monopole, for which we have an analytical solution, we can solve for it. And then we have operators that are basically able to move this monopole up to any higher multiple. It's just operators, no? Like in quantum mechanics, basically. There is nothing there. Plus, we have some kind of horizontal symmetry. So if we are able to find that there are conserved quantities between for a given multiple, that implies that since they are conserved, so it doesn't depend on radius, they are true at the horizon or at the where I put the boundary condition and at infinity. So since the game here is to compare growing and decaying mode at infinity, if I have this quantity, I can actually associate charges, and this will actually tell me a lot of properties, for example, with the symmetry of the system, will be useful also for observer at infinity, because remember, for example, in black holes, we are throwing things to this object and we are seeing how it responds. We're not going actually onto that object. So that's why this is important and interesting. And also we can get a lot of analytical properties of the system without actually solving the equation. Because you see, once we solve for the monopole, we get all the power of multiples. And this is what people do in black holes. It's a typical thing that one does when we want to study the log numbers. So we did the same for at least this one for the polar case. So we have our Hamiltonian, we write it in this way. And what we want to do in order to find the ladder operators, for which, by the way, we were not aware of a practical way of constructing them. So we had to engineer a little bit our method. Maybe you know about how these actually are constructed, but we didn't. And so the way is find operators such that this relation occurs. And these operators, basically what they're doing is basically going up onto this ladder. So A plus takes a solution to a multiple L, and it sends it to a multiple L plus whatever, N. Black holes is A is 1. We'll see that in this case, it's not 1. And not only that, we don't have one ladder, we have two different ladders. So we have two different sets of operators that are moving multiples up and down. How does that work? So first of all, and this simply comes by solving this equation. The equation is giving you the fact that we have two ladders. One ladder is jumping of 4 steps. So if you take a multiple L and you apply this operator, then you will go to L plus 4. So this means that if I am sitting in the monopole, when I apply this, I will go to L equal 4. So if I sit in the dipole, I go to L equal 5. And this is basically a structure. I take whatever function, whatever multiple L, and I can go backwards using A minus, or I can go upwards using A plus. And higher, go up and down. Okay, so this is basically moving multiples. Remember that the trick and the idea is I have a solution for a given multiple, and I can move up and down, so I don't need to solve for every multiple. Because once I have the solution for one, I have all the information about all the multiples. So the basically implies I don't have to solve every time the same equation. Possibly one interesting thing is the fact that we also decide this ladder is jumping of 4. We also have a small ladder, which is actually an automorphism between the first 3 multiples. So this basically, as you can see, N cannot go above 3 because otherwise N must be positive. So otherwise this will become giving you negative multiple. So basically what it's telling that this small ladder is moving the monopole to the N equal 3 and the dipole to N equal 2. So since you can move in here, then using these other operators, you can actually raise the monopole, you can raise the dipole, you can raise the equal 2 and the equal 3. So you can get the whole tower, but not in a straightforward way as in black holes where you take equal 0 and you go to 1, 2, 3, 4. In this case, you jump in this way. As I mentioned before, one of the ideas is to exactly associate the vanishing of the polarisability and the susceptibility to conserved quantity and charges associated to this conserved quantity. When I was reading here, so you can see these charges can be also constructed from the monopole. You can go up to any multiple, and they are conserved in the sense that they commute with the Hamiltonian. This is actually a standard thing as you can do in quantum mechanics. And these quantities are conserved. So if I'm able to find the reason why certain quantities vanish in this case, I can actually elevate it to all the other towers. So the reason is that if I am able to tell that the dipole or the monopole vanishes, I can tell which is the tower of multiple that vanishes also for higher multiples. So it's a typical thing. We compute, then since this is vanishing, then any other operator that is increased also preserve this quantity. So if I have a conserved quantity I give an L, this quantity will be also conserved at higher level. So we can construct conserved charges everywhere. And this is basically what we do. You take a solution, in the case of the dipole, you find the solution, you apply this ladder, you take the dipole, you go to the L equal 2, and then use the big ladder to go all the way up along this side. And since these two are not the kernels, okay, you can just go up every time you want, and growing and decay modes, the polarizability does not vanish because I have both modes. Both modes means that I can actually compute the analogous of the log number, which in case is the polarizability. So since I can compute it, it does not vanish for these multiples. But what happens if instead of going first to L equal 2, I just take the dipole and I use the big ladder to construct my tower. So in this case, I can go to 5, but we go to the multiple 5, and the action of A plus only gives the growing mode. So since I only have the growing mode, in this there is no decaying mode, so when I take the ratio, this is actually going to 0. So this is basically the reason why all the multiples which are odd, for the moment we only have this series, have vanishing polarizability. And it's simply related to the existence of conserved charges, which turns out to be trivial in this case. Okay, so you can do the same thing with the monopole, which I will not go with that, but the analogous monopole, so you actually complete the full tower of odd multiples for which the polarizability vanishes. So this is basically the summary of everything you can do with the ladder operators and which are the charges. I would like to focus only on this one, which is the one I described. So you see, this arrow, for example, we want to start from the regular solution of the dipole. So this A plus brings you to the kernel of this. So you find a regular solution, but it will be only the decreasing mode. And if you want to go backwards, so let's say you have a certain multiple, you want to go all the way down along this using this ladder, you will see that at some point when you get to L equal 5, if you take A minus, as you can see, we will not go to the regular solution, we go to the singular solution, which has a null charge. It's a kind of complicated structure, which seems to indicate that the existence of trivial charges, as you can see, charges that vanishes, are actually the responsible for the vanishing of polarisability and so on. So notice that this is, and with this I will conclude. This is only for the polar sector. Something similar can be done for the axial sector. So this is something which is complicated. Maybe I don't pretend you all understand this table. It took hours and hours of discussion trying to find the best way to visualize this. And I can figure out what it is because I've watched this like hundreds of times. But the idea is exactly the same thing as people are doing in black holes. So the idea is to find if the vanishing of polarisability and magnetic susceptibility, as well as the log number, can be associated to the existence of extra symmetries in the equation. So once you find extra symmetries, you probably can associate this to the vanishing of log number. So the idea is then, once you have all this machinery, ask the question, which is the underlying symmetry that you can have, and it can potentially tells you more about this, the fundamental nature of these theories. So basically, this is what I just said, and I leave you with the conclusion that we just leave it there.
Have a good summary, William.
Yeah.
Thank you. Yeah. Do we have questions?
Yes.
Okay, so on your motivation, you were saying you want to construct something that maybe pushes something at far distances. But as far as I can see, or as I understood, actually your force still decays at large distances.
So yeah, so I think I don't have slides here. So this is something they want to imagine the following situation. So as long as objects, let's say we take two objects and we took them far apart, of course these two objects will interact, and so there will be a force that driving them far apart. So there's a pushing away one of the other. Asymptotically, when they're far away, this will be Maxwellian, because the long force distance would actually cover Maxwellian. But when the two are sufficiently close such that the screening radii overlaps, then the force there is suppressed. So basically, there will be no force at all. So which is basically the standard idea behind screening mechanism. So if they are sufficiently close, you don't see this force because it's suppressed. Actually, maybe so okay, here. So basically, you want so these two objects will feel the repulsive force because they are far away from the screen. So the force is not screened. So even though it's Maxwellian, it's not screened, it's there. While in this case, there will be no such form because it's suppressed. Okay. So in that case, the gravity, if you want inside the screen, basically the electric field will be a constant. So there will be no force associated with it.
Okay. But is there a point or a radius where kind of the force, the repulsive force becomes maximum?
Yes, because you can see, well, you can see, for example, from here, I think. Or maybe it's even better from here. So at some point, you see when this becomes very large, this goes to, well, it's small. So yes, the force, so as soon as you get outside the screening, then we start getting closer and closer to the Maxwellian behavior. So I guess it's the peak would be closer to this position. So where there is this transition between the screen and non-screen region. So I think you can simply plot this function and you can see how it goes.
Okay, but this function has a maximum at x equals 0.
This function, no, x equals 0, it's 1, then yes, in the case, yes, so it's there. So because it goes this, because, okay, so it goes basically like this, as typically does in Born-Infeld.
Yeah.
So, but that is constant in the center, so you shouldn't have that force in there.
So isn't the force proportional to E?
Yes, it's true. That is true, but we do not expect to have any force in there. I will think better about it, but I think that is the case. That is the case. So you see that there is some, because there are vectors and lines here, so there is the vector in there. Yes. But nonetheless, once the two, because the only point where the force vanishes is around here, where the two are actually compensating. The thing I have in mind is actually slightly because I was thinking more about the cosmological screening, where you actually there you don't have the you don't have the force. But it's true that the electric field becomes constant. It's just not diverging. It's not it goes to zero. Yes. So.
We have more questions.
May I have one for, have you ever seen this ladder structure, multiple ladder structures? So I don't know if people have worked in black holes here, maybe. I don't know if you ever had encountered any structure like this, because we were kind of surprised to find such a multi-ladder structure. You know, maybe it's me.
This really message the formula you get for D and the superposition you can do of say point target.
Yes.
But you have this theory, something like Coulomb or Birkhoff theorem, which a spherical solution out of the body would be the same as the point charge, so that the screening mechanism continues to work with extended objects.
Let's see, because this is non-linear, so I'm not sure whether the Birkhoff theorem still holds.
But then the question would be like, can you comment something on the screening if you don't have point target or with extended object?
No, that we don't. We didn't treat that particular problem. So for the moment, we are simply discussing objects which are point ones. So I think that if you're having extended objects, in principle, there is one. Right, you should first study what happens at the interior, and then you have another surface where you could put your boundary condition, which is the surface of the object. To sort everything and to see how it happens screening and so on and so forth.
Yeah, but if the solution is the same outside an extended spherical object, then the screening will expect the same.
The typical thing is, so if we put like a, let's say we put a test particle somewhere and so on, we put it here, it will feel like, even if it is an extended object, it will see just the point, as a point source. Because it's living outside here. And here is Maxwellian. So most likely you simply feel just as the force was centered in one point. While if it is inside the screening radius where the dynamics is really non-linear, then there I don't know. We should check.
More questions?
Once you solve the gravity, can you find any readings of the gravity?
Sorry?
Once you solve the gravity, can you find any equations of the gravity? When you
So if I switch on gravity, yes, but I think I checked, and for them, so in this case, for example, log number, so there I can give you two answers. So in the case of Born-Infeld gravity, I think that the log number vanishes. So the thing that is not, to me, which I don't know, I think people maybe have investigated, is what happens if you have something which is charged, like a charged black hole, and you also have external an external electric field. So in that case, maybe the log numbers will not be zero. I know that for Kerr black holes, they still are zero, but if you charge, I'm not sure.
I'm asking.
Yeah, so I don't know. So for gravity, we didn't try. So we just like, especially because we don't, so in this case, we don't have in mind compact objects. It would be more like extended objects. So far, they are just a point particle. But even though we had in mind is, for example, dark matter halos, that would be the generic picture. So what we will be studying is how, for example, if we have a dark matter halo which is moving, will be deformed by the electric field of another nearby object. So
Of course, if you have mass, gravitation, everyone forward,
of course. So in principle, if you can form compact objects which are charged because the Earth is charged, and with that case,
with more mass.
at some point we'll get absolutely. I'm just saying that we didn't investigate this because we were not really. I know that there are papers where they have investigated how a black hole responds to external scalar vector and tensor fields. But I don't know if they've done it also for charged black holes.
More questions? Maybe I can ask one very naive one. At some point you showed this like this action and you say you take perturbation of the second order.
Yes.
How difficult is it to go beyond, or does it even make any sense within this scenario?
Well, typically this is since we are looking at small perturbation, we're just going to second order because when we want to start phonons and so on and so forth. Higher order would at some point also mix modes, I would say, because you would have nonlinear terms. And at that point, maybe it's more worth it to have a full nonlinear. Because so since for this you can actually have full solutions. Maybe it's worth it to deal with the full theory rather than the so the reason why one stops here in this case is because you're looking at small external field. So for that you have small deformations and you can actually see how these objects move. Basically, it's like a theory for linear perturbations.
Okay, thank you.
In principle, you can put this in a code and you will give you all higher terms. But then we started mixing and
Okay. Thank you. Any other questions? Last chance? Okay, not then let's thank us for the game.
If you enjoyed the video, like and subscribe.